So a couple of the common uses of alpha radiation is actually in smoke detectors and also in internal radionuclei therapy. So let's consider smoke detectors first. Smoke detectors make use of the radioactive isotope americium-241. Now, americium-241 is very unstable, and so it's not found anywhere in nature. It actually has to be created in nuclear reactors for its use in smoke detectors. So americium-241 is a source of alpha radiation. For practice, let's write down the equation of the decay of americium-241. So we can write this as 24195 Am, which is the symbol for americium, turns into an alpha particle, which is 4,2 helium, and then you can see that the atomic number needs to be 95 minus 2, so 93. The 93rd atom is neptunium, so we have Np as the symbol that is used for neptunium, and then you can see that the mass number needs to be 241 minus 4, so that gives us 237. So now we've written down the equation for the decay of americium-241. So what happens in a smoke detector is that a battery applies a voltage, a potential difference across two metal plates. So we have a positively charged plate and we have a negatively charged plate. We then have our americium source, which shoots alpha particles between these two plates. Now, because alpha radiation has a high ionizing power, as it passes between the two plates, it collides with air. And air consists of nitrogen molecules and oxygen molecules. So as it collides with the nitrogen and the oxygen, it tends to ionize these particles. And so we get a steady flow of negative charges up to the positive plate, because opposite charges attract, and of positive charges down to the negative plate. And so the smoke detector registers that as a small current. Now, if there's a whole lot of smoke in the air, then as the alpha particles travel between the two plates, they actually get stopped by the smoke particles. They get absorbed by the smoke. And so this means that the ionized oxygen and nitrogen stops getting to the two plates. And so that current, which the smoke detector was detecting, stops. This is what makes the smoke detector go off. So beep, 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 because it now knows that there's smoke or something in the way, and so it gives us a warning. So it's that ionizing ability of alpha radiation which makes it so appropriate for its use in smoke detectors. Now, another common use is in internal radionuclide therapy, which is also known as brachytherapy. This is an appropriate treatment for some cancers, such as cervical, prostate, breast and skin cancers. In this therapy, we have a very small implant which is filled with the alpha source. Now, we can have quite a high dosage in this case because the penetrating power of the alpha radiation is not very high, so it can't travel very far through your body. So wherever you put that implant, it's only going to affect tissue in the immediate vicinity. And so doctors insert these little canisters filled with the alpha sources into the center of the cancer, and then it emits the alpha radiation, which is highly ionizing, and so this tends to kill off the cells. Cells which are dividing are particularly prone to the destruction of ionizing radiation. And so since cancer cells tend to divide more rapidly, they're even more at risk from being damaged by it. So this is a good way to kill off small tumours because we can use a very high dosage quite safely, and it's a very localized effect. Beta particles are used in a couple of ways in medicine. One of the most famous ways is the PET scan, or positron emission tomography scan. So in a PET scan, we're actually using positrons, which are the anti-beta particles. So it's still called beta radiation, but it's the positrons that are emitted rather than the electrons. So how these scans work is that patients are given a substance such as glucose, which is commonly found in the body. However, this glucose or other sugar is made with a radioisotope. So carbon-11 or oxygen-15 are often used. So this is injected into the bloodstream of the patient. It then makes its way through to the organs with the highest amount of blood flow. So this can be very good for brain scans because a lot of blood goes to your brain. The radioisotope then has a very short half-life, typically less than 2 hours. So there's a couple of reasons for this. It means that the radio source doesn't stay in your body for very long. After a few days, you won't have a detectable amount there. It also means that while the scan's going on immediately after the injection, then you've got a fairly strong source in order to detect the radiation. So you get injected, it goes through to your high blood flow organs such as your brain, and all that time the radioisotopes are decaying. And as they decay, because they're beta decay, they produce positrons. Now, the positron is the antiparticle of the electron. So if a positron and an electron meet, then they completely annihilate each other. Their entire mass gets converted into energy. And it's actually this energy which gets released in the form of electromagnetic radiation, which is picked up by the scanning equipment around the PET scanner. So this then lets the doctors get a good idea of the high blood flow regions inside the patient, and they can use this to model what's going on in the human body and to see if something is going wrong inside. Beta particles can also be used to treat cancer in a similar way to how we use the alpha particle sources. So beta particles beta source emitters can be loaded into small canisters, which are then implanted into the cancer. And as these decay, emitting beta radiation, the dividing cells are especially affected by it. And so the cancerous cells, which divide more rapidly, are the most affected. So the beta emitters can target larger cancers than the alpha emitters because there's more penetrating power. But this also has disadvantages because it means that it's more likely to target healthy tissue. And so beta particles or beta emitters are only used sparingly in medicine. Gamma rays are used quite a lot for scans in medicine. So we're going to be talking about how technetium-99m is used. But gamma rays can actually also be used as what's called a gamma knife. So in a minute we'll have a look at that as well. So technetium-99m is an excited nuclei that wants to emit a gamma particle. It has a half-life of approximately 6 hours, which makes it very suitable for medical scans because it means it's not going to stay around in your body for too long. So in medicine, people attach the technetium-99 isotope to a pharmaceutical product. And that product has been designed to target whichever organ or bit of tissue in the human body that you want to look at. So bone marrow is a common example. And so this is injected into the patient, wait a while until that pharmaceutical product enters the appropriate organ or tissue, and then the patient is put in a scanner and the gamma radiation is detected. And this can build up quite a detailed picture of what's going on inside those tissues or organs, and so it can highlight any problems with them. Now, a gamma knife is a relatively new development in medicine. In a gamma knife, the doctors use a cobalt-60 source. They actually have about 200 of these sources, and they're very good for very targeted radiation therapy. So these can be used to target brain tumours. So the patient would lie down, they'd then have 200 of these gamma ray sources coming at them from different directions. Now, these gamma rays will travel as rays, and they're going to intersect exactly where the tumour is in the patient. And so individually, these gamma rays are not very damaging, as they've got a very low ionising ability. However, when you have 200 of these targeted rays all hitting the same location, that starts to cause damage. So this is a very effective way of killing off a brain tumour and doing very little damage to the surrounding tissue. And it's a lot less invasive than having to do a surgical procedure on the patient.